I'd like to offer a whirlwind tour of boundary testing, a little bit beyond boundary testing of equivalence classes. Although certainly the most popular type of boundary testing is to take an equivalence class which has a range or a continuous range and study the behavior on the extremes, right? The minimum value, the maximum value, in the 3-point case, minimum just above, just below, max just above, just below. In the 2-point case, min just below, max just above. But that is just one type of boundary. There is tons of boundaries. We held a conference about 2012 in Seattle where we studied boundary testing, and we identified hundreds of boundary tests that are all perfectly legitimate, relevant, interesting problems that show up in software engineering projects all the time. So this short survey is going to walk you through a bunch of different types of boundary tests over and above just equivalence partitioning. Little overview. So first of all, the notion is, what's a boundary? And there's a lot of different concepts people have about what a boundary is. Some people think boundaries are extreme values, the mins and the maxes. Sometimes people think boundaries are points of singularities or discontinuities. Certainly, boundaries are points at which the behavior changes or should change, or maybe should not change, but it's a point of inflection of some sort. So something is going to change at that point. That's what the boundary is, a point where there's going to be some sort of behavioral change, or there could be. So what is a boundary test? Well, it could be a lot of things. Boundary tests could be capability tests, right? We could be confirming that the behavior of the system works well at extreme values, lower and upper bounds, edge conditions. But we can also explore boundaries. Boundaries sometimes are illusions. I like to point out that if you look at the junction of two walls, or the intersection of two walls, and you visualize it, it looks like there's a clear line segment between the two walls. And yet, if I was to ask you which wall is the line segment in, so for example, this line segment here, is it in this wall or this wall? This line segment here, is it in this wall or that wall? You may want to say it's one or the other or both. You'd be correct in all cases. You might even be correct to say in neither, because it doesn't really exist. It's sort of an illusion. Boundaries are tricky things. This is the famous Necker cube, where you can draw this, but depending on where your eyes fixate, you can see that the front of the cube could either be this box here or this box here. And it's the same cube represented visually here. And it's just showing that your mind is playing games with you a little bit on what is the boundaries and what is the shape of the actual object that you're looking at. A boundary test could be confirmatory. So does the behavior match expectations at the boundaries? It could be exploratory, where we're going to learn what is the boundary. We're going to learn the point of change in behavior. We're going to study the system to try to learn what the boundary is and how the behavior changes at boundaries. Boundary tests are important. I guess we've got a lot of experience in software engineering now about boundary bugs. They happen all the time. They're sometimes they're considered the best tests. In fact, people who study what they call domain analysis in test design, study a lot of equivalence partitioning, they often argue that the best test to choose from an equivalence class is a valid boundary test. That's an interesting thing, because they suggest that that one will demonstrate that the partition works and will expose bugs at the same time. So that's, some people think boundary tests are actually the best tests. I find boundary bugs all the time. There's different approaches. You can look at boundaries in terms of the analysis of the variables in equivalence partitioning, in the analysis of the usage in terms of usage scenarios, in the variance in things like non-functional things when the behavior starts changing. If you look at this picture, this is a postal envelope size model where you can see there's a lot of different sizes of envelopes, and each one of them has a inscribed boundary, right? They all fit into different boundaries. And this is interesting for stuff like postal rate calculators to try to figure out what size your envelope is. And if it exceeds a width or exceeds a height or it exceeds a weight dimension, you may have to go into a different postal rate, for example. The boundaries you look at for postal rate calculation typically for envelopes are length, width, thickness, and weight. And there's some very intriguing things people do. Like if you look at this, they say there's like standard and non-standard. So standard envelopes and cards, they give you specific dimensions. This is the standard. If you fit within the standard, you have a standard postal rate. But if you don't fit within the standard, then you have this area called non-standard. And if you take a look at this, the minimum length for non-standard is the same as the minimum length for standard. The minimum width for non-standard is the same as the minimum width for standard. The minimum thickness for non-standard is the same as the minimum thickness for standard. But the minimum weight for non-standard is different from the minimum weight for standard. So it's really interesting because you always look and say, why is that higher? If it's out of range, shouldn't it be the same or lower? And it's I find it's amusing, but this of course probably has to do with backward compatibility in rate calculations of the postal service. There's also boundaries that come from things like precision of measurement. This is interesting when you start looking at people who are interested in precision and doing things like measuring physical phenomena or things like voltage and stuff like that. And you'll see that they always put accuracy specifications. So they say, okay, it's between 4.994 volts and 5.006 volts, plus or minus 6 millivolts. It's very interesting, the ranges. So you can sort of now can imagine testing on those extremes to see if we actually match those ranges. When you're looking at precision also, if you're using a computer, and most of us studying software engineering are using a computer, you realize that the computers represent numbers. They represent numbers, usually numbers that would have a fractional part are represented using what's called a floating point notation. Floating point notation allows us to have a very, very wide range of values. But if you take a look at a value stored in a floating point number, you're going to find that the difference between them is different. It varies depending on actually the magnitude of the variable. And some people like to say that there's also something called the machine epsilon, which varies depending on the technology and the programming language. But the machine epsilon is effectively a distance between two numbers that is discernible. So if the distance between two numbers is less than that, the numbers will round to the same value. So they basically say what's discernible. And they have actually, depending on the type, different calculations as to what the machine epsilon would be. And it's sort of intriguing to look at. It depends on the coding, of course, of the variable. And there's different ways people calculate it if you're into computational numerics. But this basically is something about precision. So two floating point numbers to be considered equivalent or so-called equal, actually you look at the absolute value of the distance between them, and if it's less than epsilon, you would suggest that the two numbers are the same because they're going to have the same floating point representation. Boundary risks have been there for a long time. Now, in the early days of boundary risks in my career, I always thought, we've got to get better at the requirements. We've got to have less ambiguity in our software requirements. But in the 1990s, after working on some very interesting web browser and web editor projects in the multilingual space, I found fantastically unambiguous ways to describe requirements so that the boundaries were absolutely clearly stated and unambiguous. Sort of a tabular style of requirements makes the boundaries really, really clear. Now, even though we had very, very clear boundaries in the software that was developed, there were still boundary bugs everywhere. So it is very intriguing to sort of say, wow, we had boundary bugs in systems that had really, really good requirements. And I started to realize that it's not really how well written your requirements are. It's that once you've got two or more people working on the same project, people are going to interpret things differently, possibly because boundary interpretation is cognitive. There's some sort of cognitive element to it. But it's very possible we have a misinterpretation of the boundary. Look at where we can have all those misinterpretations. So the boundary risk, we could have the requirement might be misinterpreted, the way it's programmed might be misinterpreted, the way it's tested might be misinterpreted, whether it passes or fails the test might be possibility, and then if it passes or fails, maybe we're interpreting the results wrong. So you have all sorts of places, all sorts of points of interpretation, and this leads to tons and tons and tons of possible boundary problems in a system. Now, boundaries are not just extreme values of input variables. They could be places where the behavior is different. If you remember your calculus, you have a point where there's a discontinuity. So the value as you approach x0 from the left is different from the value as you approach x0 from the right. So that's a discontinuity. Or a singularity, something like we're getting to infinity at this point. It's going to be undefined at some point. It's the nexus, it's the undefined point. Sometimes there's a behavior change. So if you look at this, is basically solenoidal, getting closer and closer, and then all of a sudden you hit x0, bam, it becomes an exponential decay. So the behavior is changing after that point. This discontinuity we already had, the jump discontinuity. Removable discontinuity is when the space between them is different, so you can actually say that you converge on one point. It's just that, of course, in this case, the first derivative is discontinuous. In conic sections, we have boundaries that are used to define different types of geometric objects. For example, the intersection of a cone with a plane gives you parabolas, circles, ellipse, hyperbolas, depending on the interaction. So this is conic sections are actually boundaries. We can use boundaries to help guide us in calculating things. I learned when I studied numerical methods to solve differential equations, there was a methodology called the Newton-Raphson approach. And you start with sort of a wild guess, and then you keep guessing, and you get closer and closer until you converge on the answer. And that convergence is going to be the boundary of some sort of roots. In fractals, you have things that look like boundaries. I don't know if they are boundaries. It looks like boundaries where the behavior changes of a system. We can have a signal. We can have a signal that looks one way in the time domain and a different way in the frequency domain. And so you can imagine you can have time domain boundaries or frequency domain boundaries that are different and interesting to study. I loved when I was studying electrical engineering to look at signals in the time domain, nice sinusoidal things, and then look at them the frequency domain, and there were spikes and steps and all sorts of totally different behaviors. There's political geography that leads to interesting boundaries that are very important for us, actually. If you're doing transactional systems, logistics systems, shipping systems, things like sales tax rates and rules and business rules change as you cross political boundaries. So some transactional systems really, really care a lot about political boundaries. If you want to worry about political boundaries, check companies like ExxonMobil in the States, where they have to worry about political boundaries to the point of literally the municipality in which they're selling fuel, because sometimes municipalities have special taxes that you have to keep track of and pay just for that municipality, and that has to be auditable against that municipality. Think of the entire world that they're selling fuel in and how they have to keep track of all this regional variations based on local tax laws. It's huge, the impact of political boundaries on processing. A wall, boundaries, geographical boundaries, physical geography. I love the sort of boundaries that happen when the river just jumps down. That's Horseshoe Falls, Niagara, Ontario. Boundaries beyond which dragons exist. There be dragons beyond these points. Always people would say there's a point we know and a point we don't know. And if we go beyond what we know, we may get into danger and risk. Boundaries, we're afraid of going over the edge. If you believe that the world is flat, going over the edge would be a rather risky thing. Of the edge of the earth, your ship will fall down. There's other boundaries that haven't happened because of concerns of factors in bridge building. For example, in 1916, the Quebec City Bridge collapsed. Actually, during its construction, it collapsed twice. And both times it was because they were trying to build a cantilever bridge across a river. This, by the way, does exist today. It's there in Quebec City. They finally succeeded in building that bridge, and it is the world's longest cantilever bridge. It's also the last major bridge of that type that anyone ever tried to do. They went into different bridge architectures, but what happened was they ran into bugs of scalability. So just because you could make a bridge that goes, so well at a few hundred feet doesn't mean that that same design, if you explode it, will work at a few thousand feet. So this is basically, there's points where it doesn't scale. And the Quebec City Bridge was, I guess, the first one that crossed that threshold, or at least that's documented, that crossed that threshold. There's also an interesting boundary that was discovered, I guess, in 1940 in Tacoma, Washington, south of Seattle. This bridge, the Tacoma Narrows Bridge, was basically unstable during wind conditions that weren't really harsh. I mean, the wind was 42 miles per hour when the bridge actually collapsed, and it collapsed because of what was a resonant frequency. So it started to resonate, go up and down, up and down, up and down, and eventually it sort of got destroyed. Interesting that by coincidence, people with photographic equipment and video cameras were able to actually film the Tacoma Narrow Bridge collapsing. And since that time, people have started looking at the boundaries of how much stress can a bridge take in terms of resonance. And prior to that, there wasn't a lot of concern about resonance in bridge design, and that's 1940. People have been building bridges, by the way, for thousands of years. So it's interesting that only in really recent modern history did they discover resonance had a huge impact on bridge design. When we're looking at non-functional characteristics of software systems, there are certainly boundaries to them. Sometimes in non-functional testing, we study the behavior of a system and we really try to identify the boundary. For example, at what point does it get slower than 12 seconds per transaction when we're loading a system? And if it's 3,420 users, it's important to know that so that we can anticipate the capacity we need to handle transactions reasonably expediently as the load varies. So what is the boundary where the behavior starts to change, or what is the point where we can't tolerate it anymore? So what we often look at in the non-functional testing is basically a method of measurement, a unit of measurement, and some sort of goal. So this is basically just to give you an example, and there's each one of these has boundaries, right? So you have performance non-functional testing. The scale would be the time to complete an order transaction. The meter, it would be studying the transaction time from submit to completion through the GUI. And the target would be, depending on the load, between 8 and 16 seconds or less 80% of the time. Now, when you do design an experiment, what you're trying to do is find out, are we actually within these ranges, and at what point does it break from that? Boundaries exist in all sorts of places. For example, limits of impact of authority or limits of authority. I can only control certain things. I can't control other things. So there's limits to what we can control. People who do internet work on privacy today or are studying things like promoting news on social media networks are wondering about how far we can go to stop things without violating people's rights or constraints. There's limits of patience. How long are you going to try to do something? How long are you going to try to assemble that barbecue before you give up on it? And this is a limit of patience. So people have a limit of patience. Granted, in transactional e-commerce systems, if a system has my credit card number, I may wait a little bit longer for the transaction to go through, but there's a limit to my patience always. And if an application is taking too long, I might go to the competition to buy the product. There's boundaries in terms of acuity. When two things look the same, what is the visual acuity when 2 points look the same? And of course, there's all these games people play with images, right? Where you sort of look at two images and say, are they the same? And in fact, if you look at them carefully, you'll see there's actually differences. Like that point there isn't over here. this building here is missing over here. There's actually four differences. These people here are not over here. I don't recall what the fourth one was, but there's actually four differences in this. And then once you see them, they're very conspicuous and very obvious. But from a distance, it's whoa, they look the same. They look the same. So what's the point of difference? Those are the 4 points. 1, 2. Okay, so they count the top there, 2, that one, and then the people. Yep, that's it. Color, boundaries of color. At what point do we want to call this yellow or give it some different name? This is actually a boundary that I had to work on in medical knowledge-based system when we were trying to name the color of certain fluids. And it was very important to name it correctly. So otherwise the diagnostic medicine might be incorrect. So, and you look, they're all very close shades. In fact, depending on how good this video is, I might not even be able to discern them. Then there's phonetic similarity, the boundary of phonetic similarity, when two words sound very similar, like conscious and conscious. So there's basically, conscious is awake and perceiving, and conscience is meaning the sense of obligation to be good. A good conscience or a good conscious. It's very interesting that the words sound almost identical. I believe they are phonetically equivalent, and yet different words. We have also in some parts of the world where people use languages that don't necessarily code vowels. So in some languages, we don't code the vowel. So if you're doing a search for a name or a search for a term in a system that doesn't code the vowels, you basically have to look for phonetic searches. So you're looking for things that sound similar. And at what point do we make a difference of this? And I've got actually a brother who works in speech processing. He's very concerned about when two things sound a little bit different and at what point are they a bit different. There's delays, pauses and delays in middles of transactions, and how long can we wait before we sort of say, this transaction has failed, let's retry it or restart it. So there's a boundary. In security, there's a boundary. There's a lot of boundaries. The ones I used to use was I would hire ethical hackers, and then I would time how long it took an ethical hacker in a controlled lab to break into a system. And this was done over a 10-year period, a lot of systems. It was interesting to do. And also, the ethical hackers are awesome at breaking into things or on pirating software. Resonant frequencies, these are what are the harmonics. At what point do we break into harmonics? Not something I see every day, but it's patterns of behavior. What variables lead to a crash? So if you look at the boundary here, how far, like, is it going too fast, too heavy, too light? The track has only so much load it can handle. In load and performance testing, we want to basically generate load, monitor transactions, study events. There's a whole pattern of this. For example, studying processor percentage saturation, right, versus user. So at what point do we get to saturation? And people would look at this and say, well, we want to look at the point we cross 80%. So we can find in these curves here, these are different experiments we're doing. So A, B, C, D, E, F are experiments, and each one yields a different curve. And at the point of basically about 80%, you'll see that they hit at different loads. So different experiments hit the 80% point at different loads. This is another experiment for memory, another experiment for time. And you look at points where the behavior changes, points of inflection. Points, this is a memory leak you're studying, and it's going down in a sturdy curve, and all of a sudden there's this discontinuity that comes in there, and how you account for that discontinuity so that boundary becomes something interesting to study. That's zooming up on that boundary a little more. Other points where the curves are following different directions. We could have related rate problems where we have transactions that are arriving at a certain rate in a certain pattern and transactions that are being processed in a certain rate and a certain patterns. And we want to see at what point does the queue get saturated. There's interesting patterns, not patterns, but boundaries. If you're doing platform compatibility testing, let's say for desktop computing or mobile computing, you might want to say, okay, well, we're interested in a consumer market, and therefore we would like to test on platforms starting with what was the best deal at Walmart 2 years ago or something like that. And so you basically will look at what consumers were buying at Walmart at a certain time, saying that and more powerful. That will be the minimum platform. That will be the boundary for us. We talked a little bit before about precision with machine epsilon. We know that for every type of a variable, there's different ranges. So unsigned cars go between 0 and 255. Short ints between negative 32,767 and positive 32,767, signed between 0 and 65,000, etc. So these are all different ranges of values depending on the type. It's important to keep in mind that for floating point numbers, the distance between any two floating point numbers is not the same. So we actually have to be careful about the range of values represented by the same number. So here, all of those values in the number line are represented by the same floating point numbers. There's only a discrete set of possible floating point numbers representing large ranges of values. And this becomes really important in scientific calculations. This is maybe not going to show up every day in general digital computing, but if you're using computational analysis, or if you're starting to study behaviors of large systems, you got to realize that floating point numbers do have a limitation. Not every floating point value is represented by a floating point number. Now, the boundaries can exist in time, dates, causality, the truthfulness of things, ranges and formats. There's different places you get variables related to time. So you can imagine boundaries where you might want to study the behavior of your system, like how does the system behave on the first day of the month, on the last day of the month, on the first day of the year, on the last day of the year, the first month of the year, the last month of the year, first year of the century, last year of the century, first year of the millennium, last year of the millennium, a leap year, a leap century, the first hour of the day, the last hour of the day, the first hour of the morning, last hour of the morning, first hour of the afternoon, last hour of the afternoon. Then you have the leap hour forward and leap hour backward, and the leap day forward and backward, which I'm not sure about leap days, but there's also people tell me leap minutes and leap seconds. So what are these things? They're points of boundaries in time. How will your application behave at those weird times? And then there's this weird date time boundary, which is called the International Timeline. And I've actually studied up on this. It's really interesting. There's a lot of politics around why that International Timeline gets to that point and then has this really weird behavior over there. But I'm a big fan of the International Timeline, and I actually travel a lot. Over the years, I've traveled many times between Auckland and Canada, or between Auckland and the States. And Auckland is the big major urban center in the north part of New Zealand. And when you travel from Auckland to North America, you're actually crossing the International Timeline. And here, take a look at this. Excuse the sound quality. Greetings, Robert Saber here in Auckland, New Zealand. Right now, the time is 8:41 p.m. and the date is the 20th of February, 2014. I'm just going to send a short email to myself using Gmail. I'll send it to me at robsab@gmail.com. Subject, hello from Auckland. And the text will read very simply, greetings. It is now 8:42 p.m. in Auckland on February 20th, 2014. Good day, Rob Saber. I'll put cheers in there just so I have a Canadian tag in there. Alrighty, so I'll send that, and I will cancel the. Hi, this is Robert Sabran. I just got off an over 12-hour flight from Auckland, New Zealand to Los Angeles, California. I was flying NZ2, Boeing 777-300. Very nice and comfortable plane. It was a really smooth flight. Got to sleep on most of the flight.
Right now in Los Angeles, it is 3:29 p.m. on Thursday, February the 20th. And I'm going to check my email with gmail.com. So first I'll launch Internet Explorer. So take a second. Launch up the Internet Explorer. I'm at the Air New Zealand Lounge, by the way, at the Los Angeles International Airport. And click on Gmail. And I probably have a bunch of emails because I was away for a long time. I get emails from people. Okay, so there's a bunch of emails. And there should be at least one. There it is. I'll just open that up. Hello from Auckland. So I'm just opening an email that I received it now. And it says, greetings. It is now 8:42 p.m. in Auckland on February the 20th, 2014. Cheers. Good day, Rob Sabrin. So I just want to let you know that I received that email. I received that email on Thursday. What's the date here? Just a minute. Let me get the proper date. So Thursday, February the 20th, 2014 at 3:30 p.m. So Thursday, February 20th, 2014, 3:30 p.m., which by the clock is over 5 hours before I actually received the mail by the time of day clock. Well, thank you very much. Have a very, very good day. Cheers. Really?
So,
Robert.
on to the next slide there. So what happened in that particular video was, as I said, excuse the sound quality, there's an actual copy of just that video in the My Courses Dropbox somewhere. However, what's interesting here is that I sent the email to myself, and then I received it, and by the clock I received it, 5 hours before I sent it. And I love this type of thing where you can have a transaction that crosses an international time boundary. And there's so much software that has been written with a bias that everything's taking place like in some sort of simple uniform time zone. But the fact of the matter is people move around and transactions start in one time zone and in another time zone. And so you have this notion that you can actually have by the clock transactions that end before they started. So this now becomes interesting when you look at aggregation, for example. People are looking at transaction timing, how long it took a transaction. And a lot of the query systems I've seen would have actually made that a negative number, so that it would have said, well, that transaction took -5 hours, and that would make the average really get distorted quite a bit. So when we cross time ranges, we get all sorts of weird behaviors. There's stuff that's fun. The hour crossing, except Newfoundland, which is off by 30 minutes, AM/PM zones. You're in the morning at one time of the transaction, in the afternoon for the other, and you can flip. This has happened to me often in the States where I'm working near Chicago, and between Chicago and Indianapolis, you cross the time zone and you flip back and forth between them. You don't know if it's morning or lunch, which is great because you get to eat twice. Day, you're crossing day, year, month, centuries, millenniums, all these weird time crossing ranges. So boundaries can show up in systems of equations where they intersect. They can occur in text strings. This is not the type of string. I'm talking about text strings. Strings can be a certain length, and we can basically look at the boundaries in terms of length of strings. We can look at boundaries in terms of correlation of strings. What's the first one alphabetically? What's the last one alphabetically? What algorithm do we apply? How do we distinguish uppercase and lowercase? How do we distinguish accented letters or not accented letters? How do we consider multilingual insertions of one language string into another thing? For example, the name of a hotel or something like that in another language. And syntactical elements of text. What's the shortest possible string and longest possible string that can be fit in a string, in a field, in a syntax? Then we have interesting text boundaries when you're dealing with multilingual bidirectional text. Now we talk about bidirectional text. Let's say that you're doing work in a language that uses Arabic text, and the text is general level direction of text is from right to left. So you do right to left, everything is moving fine. Then you basically type in a number. Very often in right to left universes, the numbers are still entered from left to right. So you have basically, you change the presentation direction. That's a boundary. Or when you enter, for example, a Latin-based language string, like maybe the word Google in English, in a text that is predominantly right to left, you get different behavior patterns. So where you switch between left and right to left text at the time where you point into either a change of language or changing from numbers to text, all are interesting boundary points. There's also boundary points in text of processing if you're using a language which has mandatory ligature handling. Like, for example, some practices of Arabic always have lam alif characters written as a ligature. And so that point is like a boundary because the processing of text would represent it or render it differently. And different languages have different rules about these things. So there's boundaries there. There's, I guess, a frontier, never-ending thing. Maybe there is a boundary out there. You never know. Their mission is to boldly go where no one has gone before, to see if there is indeed some limit to where we can go. I think in software, there's a lot of different places where boundaries can nab you. And when you're implementing processing, it's important to look for them and to consider. Hopefully this section showed you the wide variety of boundaries and how there are points where the behavior could change or points where maybe it shouldn't change, but you're observing that it does. So consider not just the boundaries from the equivalence classes, which are I guess the usual suspect, right? But also other boundaries. Buzz Lightyear, to infinity and beyond. All right. Well, I'll conclude with that quote, because maybe infinity is also a boundary. Maybe that's a singularity that we've got to discover somewhere. Take care. Thank you.